This is lecture 9 of Condensed Matter Physics 1. And in this lecture, I am going to solve some problems based on free electron model that we covered in the previous 4 lectures. Problem 1 is connected with Paulis exclusion principle, and it asks what is the maximum value of wavelength that can be absorbed by electrons confined in a box of length L. Remember, I had used this problem to show you that it is only very small number of electrons that participate in thermal process. So, it is exactly the same thing. If I have a box of length L, so there are these levels which are filled by electrons. I am taking number of electrons to be n, and each one carries 2 electrons. So, let us take for ease number of electrons to be 2n, then n of these levels will be filled. Now, if I were to excite an electron from here to here, I cannot do that, not an allowed transition. Why? Because the level where I am sending the electron is already occupied. So, the only electrons that can be excited are right here on top. So, the smallest frequency which is angular frequency will be when the top electron moves to the next level. So, omega would be 1 over h cross, the energy difference is going to be h cross pi square over 2 ml square, and the level is moving from n plus 1 to n square. So, this is going to be omega smallest, which is h cross pi square over 2 ml square times 2n plus 1. So, lambda maximum is going to be c over omega smallest, and that is going to be 2 ml square c over pi square h cross 2n plus 1. Anything else, if there are more other transitions, frequency is going to be larger and lambda is going to be smaller. So, this is the smallest frequency that can be absorbed. This is just to illustrate Pauli's exclusion principle to you, and to emphasize again that it is only the top electrons that participate in any excitation process of small energy. Problem number 2. A metal has electron density n equals 4.7 times 10 raised to 28 per meter cubed. what is the corresponding Fermi temperature. Tf. And second part is at what temperature will its chemical potential be 0.99 epsilon f. So, what do I need to calculate the Fermi temperature? And I want to remind you that Fermi temperature is not really temperature of any gas or any solid or anything. It is a quantity defined through Boltzmann's relationship. So, this is given as epsilon f over k Boltzmann. This is just a defined number for a given Fermi energy. Now, so first thing I need for this is Fermi energy epsilon f, which is h cross square kf square over 2 mass of the electron. And for this I need kf, and kf is 3 pi square n raised to 1/3 meter inverse, which is equal to 3 times pi square times 4.7 times 10 raised to 28 raised to 1/3 meter inverse. And this, if you calculate, comes out to be 1.11 times 10 raised to 10 meter inverse. This is the order that we had talked about when we estimated what Fermi wave vector is like. So, the Fermi energy epsilon f is h cross square kf square over 2m, which is 10 raised to minus 68. Kf square is going to be 1.11 square times 10 raised to 20 divided by 2 times 9.1 times 10 raised to minus 31 joules, and you put in all the numbers and everything, and you get this to be 6.76 times 10 raised to minus 19 joules. And you convert this into electron volts by dividing by 1.6 times 10 raised to minus 19, and this comes out to be 4.23 electron volts. So, we found Fermi energy, which is 4.23 eV, or which is also 6.76 times 10 raised to minus 19 joules. So, the Fermi temperature Tf is going to be epsilon f over Kb. You can use Kb in eV per Kelvin. I am going to use in joules per Kelvin. So, 6.76 times 10 raised to minus 19 divided by 1.38 times 10 raised to minus 23 Kelvin, and this comes out to be 4.9 times 10 raised to 4 Kelvin. Very high temperature. What this tells you is that if I were to take a gas where the energy was of the order of epsilon Fermi, I would have to have the temperature for classical gas equal to this much. Now, next I want to calculate change in the chemical potential. And if you recall from one of the previous lectures, delta mu is minus pi square over 6 kBT square over epsilon f. An advantage of writing things in terms of Tf is that 1 kb gets taken care of. So, this is minus pi square over 6 kb T square over Tf. And this tells you that T at which delta mu is going to be whatever we want to calculate is going to be equal to magnitude of delta mu Tf divided by kb 6 over pi square root. And this you put in numbers. Have I done something wrong? This is fine, delta mu is this. So, this is 1 over pi square root of 6 times delta mu I want to be 0.01 of epsilon f Tf over kb, and this is therefore 0.1 over pi square root of 0.01 Tf square. Why? Because Tf is epsilon f over kb. So, this comes out to be 0.1 I have taken care of. So, this is 6, 0.1 over pi root 6 Tf, and you put in all the numbers and this answer comes out to be 3820 Kelvin. So, you can see that for 1% change in mu, we need a temperature of about 4000 K. So, this shows you that chemical potential does not really change that much with temperature, it shifts slightly, and that is why most of the calculations we took mu to be epsilon f for even at room temperature. Question number 3. Calculate the pressure of electron gas. Now, if I have a gas of volume V, pressure P and energy U, then I know that pressure is equal to minus du dV at constant temperature, but temperature here I am taking to be 0. Even at room temperature, constant temperature can be taken to be room temperature, which is roughly 0, because Tf is almost 10,000 K. Now, the energy of electrons is going to be equal to 3/5 epsilon f, that is the average energy of per electron of electron gas times the number of electrons, and this is 3/5 n. Epsilon f is kf square h cross square over 2m. So, this comes out to be 3/10 n h cross square over m times 3 pi square n raised to 2/3, and the number density is n over v. So, this is 3/10 n h cross square over m 3 pi square n over v raised to 2/3. So, number of electrons is n, which is fixed, it is in a volume capital V. So, we found total energy in terms of volume. So, the pressure is minus du dV, and this will come out to be minus 2/3 V raised to minus 5/3, which I can write as 1 over V, and the rest 3/10 n h cross square over m. Again, I can go back here, 3 pi square n over V raised to 2/3. And because of this minus sign, this will become plus, which is nothing but equals to 2/3 u over V. That is the pressure. That means pressure is positive, the electron is gas, even if it is non-interacting, it will try to expand. Pressure is positive. Why? Because as the volume increases, the energy goes down. Even if, and this is not due to Coulomb repulsion between the electrons, we are taking non-interacting electrons. They repel because the energy goes down that way. This is maybe due to Paulis exclusion principle. Think about it. Now, what I like you to extend this problem to, what will be the equation of state for electron gas, right? Like PV equals nRT is for ideal gas. What will it be for an electron gas? Question number 4, and this is to make you realize that electrons that are participating in any transport process are actually those which are at the top of the Fermi. So, what I want to do is estimate the mean free path of electrons in a metal. Solution for this is that you see in this metal or free electron gas, all these levels are filled. So, those participating in transport process are electrons on top here, and these have a velocity of the order of V Fermi, and we had estimated these in the lectures. This is of the order of 10 raised to 6 meters per second, and the collision time, even if I take it to be energy dependent, refers to the collision time for electrons at energy epsilon f, and this from conductivity measurements comes out to be of the order of 10 raised to minus 14 seconds. And therefore, mean free path is of the order of 10 raised to minus 8 meters, or as large as 100 angstroms. So, these electrons can really move very, very far before they get collided or they get scattered. And why does that happen? You can say this is partly because or totally because of Paulis exclusion principle. These electrons cannot get scattered anywhere inside, or these electrons are not participating in any process. So, it is only these electrons, and they can scatter only to these higher energy states. So, they do not really have that many states to go to, as compared to if they were following Maxwell-Boltzmann statistics, and therefore, these mean free paths could be quite large, which is reflected in the Fermi velocity being very large and multiplied by tau. Question number 5. Is related to the way we did thermopower calculations. And it says if a metal has temperature gradient dt dx, that means temperature is changing in the x direction, show that there will be an electric current proportional to E tau epsilon f Cv dt dx, and what is the proportionality constant. So, again to make a physical picture, I have this metal and suppose I have T1 on one side and T2 on the other side. So, the electrons in this side, if you think in terms of the Fermi Dirac distribution, are more spread in energy and they are more off from equilibrium distribution, and therefore, they start moving this way. Classically, in the Drude model, it is the velocity difference of electrons due to temperature difference that leads to an electron current from higher to lower temperature. But that is not the picture when we do quantum mechanical model or Sommerfeld model or free electron model. In free electron model, only electrons at the Fermi level are participating in transportation of energy, and more importantly, the speed is Vf. So, they are all moving with this Fermi velocity. The current comes from, and as we saw in the calculation, in the difference between the distribution function f Fermi Dirac, which has slightly different shape at higher temperature compared to that at lower temperature. And what we found is that the current J is equal to K times dt dx. This is heat current, and this would be equal to number current. This means number of particles passing per unit area per unit time times the energy carried by each electron, and that is going to be epsilon f. Right. So, again compare with Drude model, where the energy carried by each electron was different. It was 3 by 2 kBt, and if the temperature differed, so did the energy carried by each electron, but not anymore. So, in a free electron model it is all EF, and therefore, the number current is going to be kappa over epsilon f dt dx. There is a minus sign here which tells you that it is in the opposite direction to the gradient, and therefore, electric current, after all, each electron carries a charge. So, electric current is going to be minus E kappa upon epsilon f dt dx. And remember, this is precisely what we did while calculating thermal power. We said there is the temperature difference gives a current in one direction that will make electrons accumulate on one side, which will give you an electric field that will drive the current in the opposite direction, and the two balance, and this gives you the potential difference. Right now, I am just calculating that current. So, the electric current is going to be E kappa over epsilon f j, the number current. No, this is J heat, because I have already calculated number current. Sorry, J heat is already done. So, this is dt dx. Okay. And you put in everything, and this comes out to be 2/3 E tau at epsilon f, because again the relaxation time is going to be that corresponding to electrons at epsilon f Cv dt dx. So, J electric is proportional to E tau epsilon f Cv dt dx, and proportionality constant is 2/3. So, that is it. I have done one problem each on the topics that I have covered. So, I will conclude this lecture with that. Problems related to topics covered in the previous 4 lectures have been solved. Thank you.